So today we are gonna move to the last portion of bolted connections or bolted joints, and specifically we're gonna be discussing bolted and riveted joints that are loaded in shear, and also the ones that have eccentric loading. So as you can see, I'm looking here at joints, bolted joints that are loaded in shear. So I have two parts that are connected. We have a lap connection, and when we are pulling on the members, we are shearing the bolts. So we call this a connection that is in shear. And you probably recall you learned about that in solid mechanics when we learned about single shear and double shear. Here we want to look at it in more details and understand all the different modes of failure to make sure that when we design these connections, we can prevent any of these types of failures. So these may be riveted or bolted or using pins. There are several modes of failure that could occur here. The first one, when we bend the bolt or the member, we shear the bolt itself, so the bolt itself may get sheared. Third one, when we have a tensile failure of the members, so I've failed the members, either the top or the bottom. We have bearing stress on either the bolt itself or the member that's bearing. So the pushing, the stress from the push of the bearing on the member or the member on the bolt, that's called bearing stress. We have a tear out, and this is if the pull would result in a tear out in part of the material that would create like kind of a slot, and we would tear the member so there is no longer a connection. And the last one is a tensile tear out. So this is a shear tear out, shear, and this is a tensile tear out. We're going to look at each of one of these modes in details. So the first one, failure by bending. The bending moment, if you look here, the moment arm between the two forces, usually these are two and equal and opposite forces. So if the force is F and the thickness of each of the members is T, we can say that the thickness between the two forces, or the distance, perpendicular distance, the moment arm between the two forces would be T over 2. So the moment then would be equal to the force multiplied by T over 2. T is the grip length, and it's the same as in this case. T is a grip length between the members. So, and is the total thickness of the connected part is most likely also T in a connection like this. Bending stress is determined by the regular mechanics of material, solid mechanics approach, where we say sigma is equal to M over I times C. I times C, where I over C is used for the weakest member or for the bolts. So we find an equivalent moment of inertia or that of the bolts to find the bending of either the members or the bolts. So this is the first type of failure, which is failure by bending. The second time would be failure by shear of the bolt. So this is like, in this case that we're looking at a simple direct shear, and we also call it a single shear in this case. We can calculate tau directly by dividing the force divided by the area. And remember, this is the simplest one. We call this direct shear. And this is the only type of shear where I simply divide the force by the area. In this case, we use the total cross-sectional area of the bolts that are carrying the load. So should there be an array of bolts, multiple bolts, I use the total cross-sectional area of the bolts. Or of course, if the force, another way of doing it, if the force is distributed uniformly, I can divide the force by the number of bolts and then divide by the area of bolt. It's the same thing. For the bolts, determine whether the shear is across the nominal area or across the threaded area. So when I use this area, should I use the nominal or the threaded? It depends on my shear plane. So is my shear plane going through a nominal area or a threaded area? And I use the area based on the nominal diameter or the minor diameter as appropriate. So this is the second type of failure. It is failure by shear of the bolt. So the first one was bending moment. The second one is shear of the bolt. Third type of failure is a tensile rupture of the member. Tensile rupture of the member. So you see, and there is another tensile of the member, but you want to differentiate between the two. This kind of tensile failure, we are failing the member across through the bolts, all the way across. And we can find the axial stress that's going to cause rupture by dividing the force by the net area. And this is very similar to what we did in solid mechanics when we find area net. So we find the width of the member, we subtract the diameters of the bolt and multiply by the thickness of the member. So we use the smallest net area of the member with holes removed. Okay. So this is the third type of failure, which is tensile rupture of member. Tensile rupture of member. The fourth type of failure would be bearing stress. And bearing failure is going to happen by crushing, known as the bearing stress. And I could crush either the bolt or the member. So the bolt or the member with the lowest strength is the one that will crush first. The load distribution on a cylindrical surface is non-trivial. So the load is distributed on this cylindrical surface. So the approach that is used customary here is to assume uniform distribution over a projected contact area where area is equal to, instead of a cylindrical surface, I'm looking at the projected. So I look at the diameter of the bolt, multiply by, so D, multiply by the thickness either of the member or the bolt, either the member or the bolt or the rivet. So T is the thickness of the thinnest plate and D is the bolt diameter. Now this bearing stress, and we like to keep it as the bearing stress, even though it has the same symbol sigma, is of course always compression and would be equal to the force divided by this projected area A that is equal to T times D. So this is bearing stress. And this is the fourth type of failure. A fifth type of failure would be a shear out or a tear out. This is a shear out and this is a tear out. So you see this is clearly shearing. The bolt is shearing the member. And here the bolt is tearing the member so that it comes out, unlike when it shears across. Okay, so shear out or tear out. And the best thing to avoid these is to make sure that we space the bolts at least 1.5 the diameter away from the edge and also center to center. So we keep this typically at least 1.5 the diameter. We want to make sure that we keep a distance from the edge of the member that is at least 1.5 the diameter away from the edge to avoid this type of failure.